Okay. Well, thank you everyone for coming to today's Corundum developer meeting. Let's go ahead and get the ball rolling on the update slides that I have for today. So mainly I just have a couple of status updates in terms of some stuff that I've been working on over the past couple of weeks, and then a couple of more things that I need to do in terms of features. So all right, so the first thing is we have new device support for the Cisco Nexus K3P-Q. Big thanks to Bob at Cisco for providing the hardware to facilitate that. I've also done a bunch of kind of hierarchy reorganization in relation to the ports. So I'll talk about that in a minute. I also did some stuff to the Pdp subsystem, fixed up some stuff in relation to the transmit timestamps and transmit completions. Also, some adjustments to the Pdp clocking infrastructure to hopefully improve the Pdp time sync performance, and a number of things that still need to be done. Then the PHY link, the PHY status registers, I've implemented some basically just RX and TX link status. The idea being that this is going to be about as generic as you can get for links, and anything beyond that I think we'll have to do through the soft core, but I've gotten that implemented in the core, although no driver support for that yet. And then I've also put down a couple of additional to-do items for MSIX and for clock information registers. So more on that in a couple of slides here. All right, so for new device support, we've added support for the Cisco Nexus K3P-Q, which is formerly known as the Exynic X100, the KU3P FPGA board, PCIe Gen 3x8, and 2 QSFP28s. And it also has 8 or 9 gigabytes of DDR4, depending on how you count, because it's a 72-bit interface. So 8 gigabytes with ECC, or 9 gigabytes with a 72-bit interface. I'm not actually sure how the Xilinx MIG handles that if you're not doing ECC. Might need to try that and see what it does. There's a couple things that are still to do on this. The way the fallback flash is set up on the board, the firmware utility doesn't have a way of supporting that. I need to do some reworking for that to work, but I think everything else pretty much works at this point. Is there anything else to mention about these? I thought the cards would be much closer to like the X10s and X25s, just with the different connectors on there, but there's actually been a number of other changes as well. So it is maybe closer to like the Silicon board, for example, in terms of, each QSFP has its own I2C interface instead of saving one pin by sharing the clock line, and a couple of other minor details. But yeah, so I haven't gotten that code committed yet, but I will be adding that in the next day or two. I just had to ask Bob about naming, so I can name all of the folders and constants and whatnot appropriately. Since it would make sense to use the approved Cisco naming instead of the old Exablaze naming. So I'll be getting that operational and in the repository within the next couple of days. I'm also preparing to just push all of the changes that I've done so far. I need to finish testing across all of the boards for that. I'm hoping to finish that up in the next day or two. All right. So getting on to some of the changes that I've made for everything. The first is a kind of port-related hierarchy adjustment. So originally, I had the port modules, or all the port-related code. This is the layer 2 ingress and egress modules, and the asynchronous FIFOs on the ports, and a couple of other things. All of this was implemented at the interface, or sorry, at the core logic level. And the reason I put it there is because I had to jump through the application section a couple of times. And I figured doing it at the core level would make sense because that's where the application section is, and it would save me having to drag a bunch of signals through the hierarchy. But I've come to the realization that it makes more sense to put it in the interface module and then just add a bunch of ports to the interface for the connections to the application section. So I've gone ahead and done that, and this simplifies all of the, it centralizes all of the logic for each interface, including the port, inside of the interface module. And this simplifies things like port control register connections. So for, I know PFC in particular, I'm going to have some mapping between the PFC traffic classes and the internal traffic classes so that everything will be handled correctly. So we need some control registers for that. This now provides a nicer way of connecting that up. It also simplifies PFC related connections in terms of making the actual flow control connections between the MAC components or the internal layer 2 data path components and the FIFOs. And since those are all sitting at the same hierarchy level, that's a little bit easier now. So the status on this is it's done. All the designs have been updated and it's tested. It works. All right. The next thing is some adjustments to transmit completions. So controlling the transmit FIFO fill level requires some sort of feedback from the far end of the FIFO when packets are actually leaving the FIFO and getting sent over the network. And originally, when I implemented the shared interface data path, I used the transmit PTP timestamp path for this functionality. So this meant that if you disabled transmit PTP timestamps, things would get stuck, basically. So what I decided to do is basically rename all of the signals so it's no longer PTP related and it's now just generic transmit completion and transmit tag. And then I added some additional code to turn around the transmit tags if you have PTP timestamping disabled. So this means that once a packet leaves the interface module for the last time after going through the application section and whatnot, then that transmit tag will be turned around and passed back down to the transmit engines and schedulers and whatnot. So with this thing, and I also had somebody ask about turning off PTP timestamping and things breaking. So with this change, disabling PTP timestamping now works again, and I've added some tests to verify that. And this change has been implemented on all of the designs, and all the ones I've tested so far work. I guess one thing I should also mention is I discovered a bug that I'd introduced when I implemented the shared interface data path, which broke PTP receive timestamps for all of the 100 gig designs. So I fixed that too. So that's good. All right. And then Pdp clocking updates. This is something I've mentioned a couple times previously. Currently, or I guess previously, the Pdp hardware clock used the PCI Express user clock basically as the reference clock. And the PCI Express clock from the host is not necessarily all that accurate. And it's subject to things like spread spectrum and whatnot. So it's hard to say exactly how stable that clock actually is. So what I've gone ahead and done is pulled out the PHC logic into a separate clock domain. And then we can run that on one of the transceiver reference clocks, which is going to be much more stable and going to be running at a much more accurate frequency than the clock coming from the host. So that's been implemented for all the current designs, and it works great. And this will potentially support things like Syncy or other solutions by allowing you to slew the transmit reference clock, which will also slew the actual bit streams coming out of the transceivers, and then you can keep an exact ratio between the transmit reference clock and the PTP hardware clock. The other thing that I did as well is I changed over the parameters used to specify the PTP clock period from like a nanosecond and then fractional nanosecond component, which directly matches what the registers are in the PTP hardware clock, to fractional definition, where we have a numerator and a denominator. And the reason I did that is so that you can actually get an exact fraction in the PTP hardware clock module, because even something simple like at 10 gig, the reference clock is 156.25 megahertz, which is a 6.4 nanosecond clock period. 6.4 is at least the 0.4 is an irrational number in binary. Irrational? I guess not irrational. It's a repeating decimal. It's like 1/3 is 0.3333. 6.4, in hex is 6.666666. So if you're just adding a constant value every clock cycle, you're going to slowly get off of where you're supposed to be. You have to add a little bit extra every couple of clock cycles. So if you derive all this stuff from a fraction, then you can actually keep track of this little remainder and keep adding that. So the clock actually supported doing that, but it wasn't used previously. So with this new fractional definition of the clock period, I have code that will automatically compute what the step size is, as well as what this little fractional remainder is. So if you leave the step size at the nominal value, then this will implement the exact ratio. So you can use that for syncing or whatever instead of time syncing by slewing just the step size of the PTP hardware clock itself. So currently not doing anything with that, but it's provides the capability, going down the road in the future. And I've also tested this on a number of boards. I haven't tested all I've not tested them all yet, and it works great. And the frequency offsets reported by the PTP4L are much lower. Instead of reporting like, I think it's reporting numbers in ppm. Instead of reporting like 30,000 ppm, it's reporting like 800 ppm. So that's a good sign. And the status of this, yeah, all of the designs have been updated. They can all build. I'm going to be testing them over the next couple of days to get everything all squared away. All right, so after getting some of this squared away, eventually I'm going to take a crack at getting variable length descriptors working, which is, performance improvement and also going to be super important in terms of higher level capabilities. Also getting the management software working, which will give more control over the transceivers and a few other things. And then 5 status registers. So I mentioned this briefly before, that what I've done so far after I did the port reorganization, I went ahead and added a couple of register blocks associated with the ports. And the way I did that is kind of similar to the scheduler blocks. I have a port level register block that doesn't have that basically defines another string of register blocks that are associated with an individual port. And then underneath that, I added a port control register block, which has status registers for TX and RX. And in these registers, I am indicating 2 different bits at the moment. One of them is the status of the reset signal for TX or RX. And then the other one is an additional status bit that I added for TX and for RX. So what you can do is set that in the board level design from the Ethernet PHY or what have you, and then it'll be indicated in these registers. And the idea behind that is, we'll have a board independent way of indicating just the link status for the driver to take advantage of. So what I have not done yet is actually implement the other end of this in the driver to actually, change the link state with at the net device level. So that will be a to-do item, but this at least works in the hardware. And so this is already live in my my development fork, but hopefully in the next couple of days it'll get pushed back into the main repository once I'm finished testing everything. All right, and then we have 10D25D switching. This one works in hardware, and this was actually super useful in figuring out the port mapping on the new boards from Cisco, the K3P-Qs, because I could flip the ports between 10 gig and 25 gig one lane at a time to make sure that I knew which lane was which. But yeah, so what we need to do with this is get the more complicated control logic implemented on the soft core once I have that working. So that's still a to-do because we're waiting on that. And then I also need to make a couple of modifications to the transmit engine to handle drop packets. It's now not just when PTP is enabled, it's now just period because of how the PTP, the transmit feedback path works now. Right. Okay, so now for a couple of new to-do things. First one is MSIX. So right now, Corundum uses MSI for interrupts, but I think it's going to make sense to move to MSIX for a number of reasons. One of them is that MSIX simply supports more interrupt vectors. MSI is limited to 32. Second one is that if we want to implement SRIOV at some point, we need MSIX because as far as I'm aware, SRIOV requires MSIX. I'm not sure offhand exactly why. It might have something to do with being able to actually specify different addresses for each one of the interrupt vectors, which might be necessary for the IOMMU or something. I'm not quite sure about that. The other thing I'm not quite sure about is it seems some systems limit MSI to one vector. And so I actually got a new computer recently, a Dell 7920 workstation machine with similar Xeon scalable CPUs to the ones that we have in the CSE building. And got it in. I put a couple of Mellanox NICs in there. I can do 100 gig, no problem between, between the two different CPUs in the machine. I can do 100 gig between two NICs on the same CPU. Everything looks good. I whacked Corundum in there. Performance was terrible. And it wasn't immediately clear as to what was going on until I looked at LSPCI and I noticed that, oh, why is there only one MSI channel active? So I don't know exactly what's going on here. I think it has something to do with the system firmware, maybe. I'm not exactly sure, but this is something that I've noticed on a couple of motherboards where that's limited to one vector for MSI. So if we move to MSIX, then it should just work. So I'm going to be taking a look at this hopefully over the next week or two and see if I can make some headway on getting MSIX working. The thing that makes MSIX a little bit more complicated is that part of it lives in the PCI Express bar versus MSI is entirely in the PCI Express configuration space. So things are a little bit different in terms of how software sets it up, and things are a little bit different in terms of how the MSI or MSIX interrupts are actually issued. So I'm going to be taking a look at that, and hopefully I'll be able to get something operational soon. It may make sense to support both, so you can use MSI or MSIX depending on how many interrupt channels you need, because MSIX will consume a few additional, block RAM resources on the FPGA. But we'll see about that. I guess the other thing is that the interface to the IP core could be a little bit different for MSIX in terms of actually issuing the operations. So I'm gonna have to take a look both at the PCI Express code, Verilog PCIe, and also the simulation models to get MSIX working properly. Let's see. And then one other thing, this is something that the folks at MLE were asking about, is to have a way to report information about the clocks and the design, and particularly the frequency of the core clock. So what I want to do is add a clock information register block, which will basically have frequency counters for a number of different clocks, primarily the core clock, and then the TX and RX clocks for the individual PHYs. And this is necessary because things like the scheduler run in the core clock domain. And if you want to do things like rate limiting, it might make sense to have a very good idea of what exact frequency the core clock is running at, so you can actually schedule things properly. The status of this is to do. I wanted to go ahead and get all the current changes that I have all pushed up to the repository before I take a crack at getting this to work. But this should not be particularly complicated to implement, and I should be able to implement this without a lot of invasive changes, especially now that I have the Pdp clocking change. So with that done, we now have a much more stable reference clock, so we could use that reference clock to measure all of the other clocks, basically. All right. Another thing that I've been thinking about doing is just putting together kind of a master to-do list effectively of all of these little things that I want to implement at some point, and put that up on the GitHub repository. And then if anybody wants to, take a little piece and work on it, then that'll be kind of a centralized list of things that we can look at instead of just having these slides. I'll probably do that in the next couple of days because I think that would be useful. I do have the roadmap, but that's kind of like pretty high level. So yeah, I'll do that in the next couple of days. I think that would be a useful thing to do. All right, and then I'm also going to go ahead and put up my to-do list for the stable release again. Haven't knocked off any more items, but just the next couple of things that I think need to be done before we start to cut version releases is to get the checksum offloading updated. And the main thing I need to do for that is to improve the parsing of the IP headers. And this will also help improve the RSS implementation as well. I want to get variable length descriptor support, and I want to get the FPGA management software working. So not very many items on this, but lots of other little stuff that's been causing these to get pushed a little bit. Anyway, that brings us to the end of the status report for today. At this point, I'll open up to discussion if people have any questions or comments or anything else. I'm not sure if Emily wants to take over the right now, or if anybody else has any questions.
I saw a bot from Silicon, which was similar to the one that supports Corundum, and also it was smaller. Do you think you are going to make it support Corundum? If you know
so
what
you're
I'm
talking about
talking
the
about, but if you don't know, I will send it.
FP2CGHH card, the half height one.
Yes, HH.
Yeah. So I think that was actually a discussion that I had with Silicon when they sent me the full height card originally. The reason we settled on the full height card, I think the project that kind of facilitated that happening was using the full height card. So we went ahead and they sent me the same thing. But yeah, potentially they could send one of the half height ones. I probably need to reach out to those guys and at some point and see what the deal is with stuff in general. Yeah, so if I had one of those cards, I would add support for it, because as far as I'm aware, it's effectively identical to the full height version, but it has 2 memory interfaces instead of 4, which so you can't use the exact same code base for it. It has to be slightly modified, but it's otherwise the same thing basically. So yeah, if I can get my hands on one of those, I'll support it.
If it supports, I think it will be more useful than the one that's being used now. Now, I'm not sure, but it might be because of its size advantage. Maybe yes.
Right. Yeah, that's possible. Yeah, I don't know if you have any contacts at Silicon, but if you do, be happy to.
In some case, some servers don't have enough space for some cards. So for full height, it might not have enough space, and it's constrained to a select server sometimes.
Right. Yeah. So we've run into this problem ourselves at UCSD, because the servers that we have are, well, they don't accept double width cards. Basically, they will accept full height, but they won't accept double width. So you can't put alveo boards in them because they don't fit.
Yes, width is also a very big problem, I think.
Right. I mean, it's becoming a little bit less of a problem with the use of GPUs in data centers. It used to be, who would put a GPU in a data center server, right? I mean, it's like the graphics cards you need in these things are, maybe for KVM over IP or plugging in a crash card. That's it. You wouldn't put a monster GPU in there. And then along comes machine learning and AI, ML, all of that stuff. And now, oh, hey, can we put 8 GPUs in a server or 10 GPUs in a server? You want to put as many GPUs in there as possible. So now we're seeing servers that are specifically designed to accept GPUs, which also means they should accept the full-size alveo boards. So
yes,
yeah, the servers we have are too old for that, unfortunately. But yeah, we can definitely support that one. It's just the standard deal that I have is that I don't support hardware I don't have access to. That's not much to say beyond that. So if somebody provides the hardware, I'll make it work. So Cisco just provided these couple X100s, and over the weekend I got it working, and that'll be live pretty soon. So, same thing for, if we can get, if I can get my hands on one of these half height cards, same thing. But I guess I will also say, short-term loaners doesn't count, because the whole point is that I need to be able to test on the card long term. So yeah, if we can convince Silicom to donate one, that would be great. So yeah, I think the only reason that Silicom donated the first one is because somebody was doing a somewhat volume project and wanted to use Corundum on that card. So if you guys are moving a good number of cards, then I'm sure we can communicate with Silicom and see if they'd be interested in providing another one. But because their goal is to try and sell as many boards as possible. So if they have a customer that's like, yeah, we'll buy 100 of your boards if Corundum works on there, then they're more likely to provide one, an extra one to facilitate that.
Yeah. And why do you think that? So you told us that you were creating registers that measures clock frequencies from different clock regions.
Right.
Will you be generating special clock which is not loaded by any other logic than just measuring, or how do you plan?
Right. So my idea, so this is for the clock info register block. So my idea was to use the PTP reference clock that that now exists, and to use that for measuring everything. So, I mean, obviously, if you're going to measure, one clock versus another clock, yeah, you have to have one clock that's kind of a known good reference. So that was kind of the idea behind behind reworking the PTP infrastructure to support running the PTP hardware clock module in a separate clock domain. Is then we can then run that using a much more stable clock. And the idea behind that is that we'll use one of the raw transceiver reference clocks. So not even after the PLL, before the PLL, if at all possible. And with Xilinx devices, you can do that using, I guess, one of the iBuff DS blocks. I would need to double check exactly what I put in the code, but yeah, so that'll give you a clock that you can use to drive stuff in the fabric based on whatever is coming in externally on the dedicated reference clock pins. So we can use that then to drive some internal logic that's then running on the much more stable oscillator. And it's not affected if you reconfigure the transceiver PLL on the FPGA or whatever. So so the idea for the clock information register block is just to use that same clock for measuring all the other clock domains. And I guess the other thing you need to know is what the frequency of that clock is. So the other clocks are measured accurately. So since I now have this new fractional representation for the PTP clock frequency, we know, or ostensibly we know that frequency very accurately. So we can use that to set things up so we can get accurate frequency measurements. Does that make sense?
Okay, yes.
Okay. Does anybody else have any other questions,
But
comments?
still, not 100. We cannot do 100%, right? We cannot be 100% sure about which one is more precise.
Well, it's more precise than the PCI Express clock because that's coming from the host.
Yes, sure, that's for
so
sure.
we know that it's relegated
Yes.
to the card. Potentially for some cards, so the other problem is that not cards don't always give you very many clocks to work with, and depending on how things are wired up on the card, you can run into slightly different configurations. So for instance, on like the I think it's like the XNX X10, basically the only clocks you have are a 161 megahertz reference oscillator for the transceivers, and then the 100 megahertz PCIe reference from the host. And that's it. There's nothing else on there. Well, actually, there might be a 10 megahertz TCXO. So you could run it on the TCXO, I suppose. or you could run it on the transceiver reference clock. So the idea behind running it on the transceiver reference clock is then if you slewed the reference clock for synchy applications, then ostensibly that's going to be even more accurate because it's now effectively a frequency reference for the network that you're synchronizing, instead of just the current PTB time. You're actually doing something lower level. So that's actually a reason that you would definitely want to do it this way and use that as a reference clock, because if you time sync that to some NIST frequency standard or something somewhere else using Synchy or White Rabbit or something, then you would have even more accurate measurements of the clock frequencies. Anyway, does anyone else have any other questions or comments? All right, I guess I noticed that Alex Badea joined us. We're going to be getting the code pushed up soon for all the changes that I made over the past couple of meetings, effectively to the core Corundum repository. Hopefully this week. Then once that's live, we can start taking a look at what it'll take to get like the what was it? The application block support in terms of the auxiliary bus and extension driver working on older kernels. So I know this is something that the MLE needs to do. I think Alex Badea in particular had some ideas in terms of how we might be able to do that. I think there was like a loadable kernel module that we could ship separately to provide the auxiliary bus functionality, something along those lines. Might be, if we have any references for that. That would
if
be
I remember correctly, I think I've seen the Intel ICE driver do something similar, if not identical. So that may be a good place to look at.
Intel which?
Intel ICE, which is, I guess, for the Columbia Hill family.
Okay.
Oh yeah.
So I guess for the core APIs of, I don't know, register an aux driver and find it and so on, that should work without any problem. The one thing that probably wouldn't work is kind of automatic loading of aux drivers based on auto detection, something like that. I think that requires some section magic that gets done when you build the monolithic kernel. But in terms of API,
loading the actual modules.
Yes,
I see. Yeah. Well, I mean,
yeah, I think that's one of the
INSMOD everything. I think that's that might be out of scope.
I think that's one of the ingredients. So I guess the main driver would say something like, I could use an aux driver for, I don't know, this string right now, and then that gets passed on to Malprobe and they get overloaded. That probably wouldn't work with an Auto3 aux driver.
I'm actually not sure if that works. Well, okay, so everything I've been doing so far has just been out of tree. I guess maybe the situation is slightly different if you're doing stuff in tree. But yeah, I guess if you INSMOD both of them, then maybe it'll just work.
Yeah, that should just.
All right. Well, I'll take a look at that then. So ICE driver, I guess not the upstream driver then, right? Because upstream driver wouldn't need that.
It's on the one on SourceForge, Auto3. I can send the link on Slack.
Yeah, if you have a link, that would be great. Because I think that's going to be particularly important for the folks at the MLE that have to run some of this stuff on like CentOS, Red Hat, older kernel versions that don't support the auxiliary bus yet. Now that we actually are going to have the code in the repository to play with, now we can try and come up with a solution for this. Yeah. All right. Well, I mean, I guess if nobody else has any questions or comments, then maybe it's time to turn it over to MLE, who I'm sure has a lot of questions. All right. I guess Ulrich, Joachim, you guys have any?
Yeah. I actually don't have a real question. Just wanted to mention, if you want to put it to this, one way could be to add requests, items, or issues. And there could also be a discussion about how to do something.
Oh, like instead of just making a list, just open up a bunch
Right.
of issues.
Right.
That's not a bad idea. Or I guess what I could do is just open up a kind of a to-do items issue, and then we
Yes,
could just edit
yes.
that one. I think there's a way to make like a kind of a checkbox list. That's a good thought. Yeah, maybe I'll do that. Might be a more appropriate place than creating a wiki page. All right.
I don't
Oh, I
know
also
if Joachim actually has some ideas or thoughts about MSIX. I guess we implemented in one
yeah.
project.
Okay.
Not sure.
I guess he's not in front of his computer at the moment. He's still muted.
Possibly.
Yeah.
I definitely remember that for the Glidings IP course, there's a separate interface to deal with. Not sure. I haven't looked at it yet. How this is handled on the native side. That could become a little bit more tricky to implement this vendor independent.
Right. Yeah. So that's what I've been kind of mulling over, but I don't think that's necessarily a major issue because so MSI, MSIX, when you're actually making the requests, it's just a PCI Express write operation. So as far as I'm aware, like for the Xilinx IP core, the MSI, when you're doing MSI and MSIX operations, you can use their kind of MSI, MSIX specific inputs, but you could also just issue the rights yourself over the standard interface that you use for issuing requests. And I think everything will just work. Not 100% sure about that, but I think from the last time I was looking at the manual, it seemed like you could do that if you wanted to. And I think that probably applies to most of the other cores as well. I know for the Intel P-Tile, they have no separate interfaces for MSI, MXIX operations. It's all implemented by, manually issuing PCI Express writes. So, that means that things aren't necessarily going to be all that much more complicated. Actually, I guess the other thing for MSIX, since basically everything lives in the bar space, even when you have an interface on the hard IP core for issuing MSIX operations, you're basically just giving it all the same information you would for issuing a write, right? You got to give it the address. I think you give it the value. You give it like I think even like TCA, TTR related to stuff, and what else? The function number, obviously. Yeah, that's important. Yeah. And then the core goes and issues that and merges it in internally. But feeding that into the core versus, adding another port on like the shim modules, that's basically the same thing. It doesn't really make that big of a difference. So yeah, I think the idea with this is there's a couple of pieces that we need. One of them is the ability to issue these separate rights for actually issuing the interrupts, and that can be implemented in the shim. I think it's gonna have to go in the shim one way or the other. So it's either gonna go in the shim for talking directly to the MSIX specific interface, or it's going to go into the shim for generating and merging these write operations into the transmit path. So I don't think that's really all that big of a deal. The more complicated part is actually implementing the registers for all of the MSI vector addresses and the pending bit array in bar space somewhere. So that's I think it'll be the slightly more complicated piece is to get that part of it working. But yeah, all in all, it shouldn't be that big of a deal. And then I think right now my PCI Express simulation framework doesn't support MSIX, so I will need to go add support for that so we can actually initialize this and use it. All right. So does Joachim have any questions or comments, or anyone else from MLE, or anyone else in general for that matter?
Uh, you do you remember you suggested me to talk with Jackson about IXY driver,
Oh,
which
right.
is
Yeah. Yeah. I think we talked about that a little bit. Yeah.
it was only a user space code without any module. So I talked to her and she told me that everything was working well without any kernel module, but yes.
Right. Yeah. Yeah. I guess if you turn off the IOMMU, then you can pretty much do whatever you want, I think. Well, actually, I guess it does depend on how you're talking to the device. I think this was something we talked about a little bit before. If you use like I'm thinking SRIOV, but not SRIOV. It's VFIO, right? And I think there's also UIO. I think these will configure the IOMMU appropriately so you can do DMA from user space. But the flip side is I don't think there's a way to use these in combination with the standard kernel driver. So I think if you're running fully in user space, then we don't need to jump through necessarily any more hoops. It's just, you don't get to use any of the capabilities of the, Corundum device driver. You have to re-implement stuff if you need it. But yeah, if you want to do a hybrid thing, then that's where things get more complicated.
Do you think if we change many things, is it better to use only user space driver, or it will be still useful to implement kernel module and plus user space? What do you think, or what any others here think? I'm
Well,
asking.
so are you talking about Corundum or just in general for
Corundum?
networking related stuff?
Both, I think
Both.
both.
Okay.
Yes.
Um,
And when one is better than the other or worse than the other, I just want to understand these things.
yeah. I mean, from my point of view, you do whatever's, the most appropriate for your application. So if you need to connect to kernel interfaces for various reasons, then it makes sense to do the hybrid driver. The nice thing about the kernel is it provides a lot of, management level stuff. So like ETH tool, for example, where you can change a lot of settings on the NIC from a user space tool. That's a pretty useful capability, being able to dump out the the optical module EPROMs and whatnot. That's super useful, but that only works if you have kernel interfaces registered for the network interfaces, and you can only do that if you have a kernel module. So, if you need that kind of capability, then it makes sense to use a kernel module. If you don't care about that kind of capability, then you don't necessarily need the kernel module. So yeah, if you're doing something that's like totally self-contained, where you don't need to touch anything else in the kernel, you don't need to touch any other hardware, fully user space driver is probably going to be just fine.
Okay, so if you don't need to use some tools from kernel, then you don't need kernel driver, right?
Yeah.
So, okay, thank you.
That's kind of the way I see it anyway. I guess the other thing you can do from a kernel driver is, you can register device files and things like that, which you can then open up from user space tools. So if you need to have several different tools connected to your device, doing different things and talking to each other and whatnot, that's kind of what the kernel is there to facilitate, and you can, register those interfaces through the kernel. But if you don't need that for your application, then that's you don't need to use the kernel module. I guess the other thing for Corundum is that there's also some shared code in terms of well, eventually there will be code for talking to like the soft cores and whatnot on the FPGA, and having to port that around in the application in a user space application. That might be additional code that you got to deal with if you're going to rewrite that, versus using the kernel module. Although I guess on the flip side, we also have the little library now, the libmqnic.a, where that kind of stuff can go as well. So you can just include that, and then you don't need to worry about code duplication. Because that's actually one thing about the Corundum user space utilities is they're kind of set up such that they can work with the driver present, or they can talk directly to the card, which is useful if you want to, run the firmware update utility without having the driver loaded, which can potentially be useful under certain circumstances.
Thank you.
Yeah, sure. Still no news from Joachim, I see. All right, well, either he can't figure out how to unmute himself, or we got nothing to add. What? Oh, there we
No
go.
news from me. That's correct. I mean,
No news. All right, no news, no questions. All right, fair enough. I know you guys got some hardware in there, so I guess you guys have been pretty busy getting some of the kinks worked out of that.
yeah. And unfortunately, I'm a bit sidetracked with a whole different project. So.
Okay. Well, I did get the PHY status stuff implemented on the hardware side, so I guess you guys can take that, run with it, and get the driver side of that working. In terms of checking the PHY status periodically and updating, the net device status. And then also the clock info block stuff will have that operational soon, so you have your accurate reporting of the core clock frequency. So I think those were the main things that we talked about either at the last meeting or on GitHub issues. So
yeah, we will have a look at that.
All right.
Definitely, yes.
All right, sounds good. Ulrich, did you have something you wanted to say? I noticed that Ulrich came off mute, but
Simon, one of our colleagues.
What? Can you say that again, Ulrich? I didn't catch what you said.
Yes, Ulrich, there is problem with your microphone, I think.
I think I lost connectivity to my wireless. Am I back now?
Yeah, there we go.
Okay, sorry. Yeah, so I guess one of our colleagues is back to working on the timing on the Intel device, and there might be questions coming up that we will ask. Right now, we are throwing in a couple of additional stages within, for example, XC-Lite infrastructure. So we're pipelining this further to relax non-critical paths. But yeah, let's see. So we already halved out the timing issues. But at some point, I guess we might some help from your side.
Right. Yeah, I guess you guys did submit a couple of modifications to some of the AXI Lite components and a couple of other odds and ends that I need to take some time and review those and try to maybe make a couple of modifications. So yeah, I think this was mainly around the memory inference, right? So to make sure.
So the patches that we currently submitted are all about memory, and this helped a lot with timing. But now we are facing kind of like classical timing issues, as our device is the slow and small one with respect to the ones usually used for Corundum.
Right.
We have to kind of spread out or help the tool spreading out the circuit across the chip. And we see some portions of the circuitry is pushed to places where it kind of has to be, but from a timing perspective shouldn't be. So we try to relax a lot of control paths that are not performance critical to help improve the timing critical paths. But yeah, we see how far we can push this, and then I guess we will add some patches that provide parameters to enable these additional pipelining stages.
Yeah, that sounds like a good strategy. Yeah, I guess one thing that I've kind of been avoiding for a long time is adding like lots of additional registers for pipelining or whatever. But I've since come to the realization that that's not necessarily the best approach, because FPGAs give you, tight coupling between the flip-flops and the LUTs, right? Basically, every LUT can directly drive a flip-flop. So it doesn't necessarily make sense to avoid adding a bunch of flip-flops because they're there. You might as well use them.
Yeah, and in some points you actually might not be able to reuse them for something else if you already used a lot right next to it. So there
right.
is some
Yeah. So it might make
limitations to
sense
it as well.
just to try to use more of them. Yeah. So
Yeah. So what we saw is the Intel tools allow for some or provide some heat maps on
oh, and then
routing
Intel also
systems.
has their hyper register things, right? Where that you get a bunch of
Exactly.
extra registers that are just all over the place in the routing.
Right. And but they were kind of restricted, so you can't reset them. You can't
reset
initialize them.
Okay.
So-
Well, so this is not so
pure
bad for the
decent
data
problem.
path stuff. So I guess that's probably kind of a good thing about how I usually design the data path components is that the data path itself is not reset. So
Right. That really helps. Yeah.
yeah, so that means they can actually be pushed into the hyper registers. There's a lot of people
Yes.
saying that it's like, hey, you got to reset every register in the design. I'm like, no, you don't. There's stuff you do need to reset, but there's other stuff that you don't need to reset.
I would say most of the registers don't require a reset, just a control path.
Right. Yeah.
Yeah. So yeah. So that's what we are looking into, and what we see right now on our devices that yeah, it's quite full from a routing perspective, and especially the long paths are pretty packed. We could add a lot of small or what is it called short paths. So yeah, that's why I think that our problem is that portions of the security is pushed around the chip with the resource constraints, and now they use the long wires instead of short wires, and we need to break those up. Or break something else up that more long wires becomes available with the important connectivity. So that there is Intel kind of provides these two views onto routing on the chip. That's the short path and long path, and provides routing user heat maps on the die view. It's pretty interesting and very helpful to investigate these kind of issues.
Yeah, that does sound like a pretty useful capability. So you can actually see not just like a percentage, here's how much routing resources utilized, but like which types.
Yeah,
long
and
versus
where
short versus
that's
whatever.
very
Yeah.
important. So where actually is the problem? It's not about okay, it's 20% or 80%. No, it's in this area, it's more than 100% used. So that's where your timing issue is located.
Right.
And you can have a look at okay, which buses are going through this region, and how can I now help them relax?
Right.
Yeah. So it's pretty interesting and it's very helpful. But yeah, you have to go through it and then iteratively timing.
What sort of resource utilization just overall are you looking at right now? You said it's pretty full. Are we talking like 70% full, 90% full?
But now that depends on type of resource. So from a block RAM perspective, we are at 80%. From LUT and registers, it's more like 50%. So that also tells like, okay, there is more flip-flops to use for pipelining.
Right. Yeah. Right. Yeah. So I guess that means maybe there's some more adjusting we could do in terms of the block RAM utilization. Just do we need that many block RAMs for various things? Yeah, that's one thing I need to take a look at some point is actually the size of the async FIFOs, because I think I can switch those. I think those don't need to be a full packet size, and that would definitely free up a few RAMs if that's changed. And you're running it with 4 ports on there, right? Basically, you got 4 QSFPs, I think, on the card.
We have 4 SFPs, and yes, we are running
Oh, 4
ports,
SFPs, that's
4
right, yeah. And you're
4
running that with
ports for
4 ports.
interfaces. And
Okay.
right now we are fitting ports to interfaces with timing, so that meets timing this design. But adding more interfaces then at some point provides issues and timing gets violated, and that's just due to obvious reasons. The circuit
So
gets
you said you have a meeting timing with how many interfaces?
2.
2. Okay. Oh, that's actually pretty good. Yeah, I just tested the. Well, I guess you guys have a bunch of modifications to improve the timing. So, because I just and the the resource utilization, because I just did another synthesis run with the 520N MX recently, and it's failing by about 100 nanoseconds TNS. So, some work to do, but at least the paths are not crazy long. So, yeah, hopefully we can get some of those changes pulled in and see how things are looking. So
yeah, I would suspect that for this big FPGA, the patches provided, if they make sense for you, they would help.
So I pulled in the patches verbatim, and that you submitted so far, and it seemed like it didn't make much difference. So I'm not sure what's going on with that.
Yeah, then there might
I'll
be
have to
some
investigate that a little
classical timing
further.
issues in there as well, like just where the transceivers are and how far the signals have run.
It's possible. Well, I guess so. The other thing that I've been bit by a few times is Intel's incremental compile screwing things up. So I may need to try doing a make clean and then rerun and see if that helps. Yeah. Okay. Oh, and the new boards that you have, how are they working? Did you have all of the kinks worked out at the board level, or do you still have some other modifications you guys need to make? Rev 2, Rev 3.
Not sure about the modifications yet. So we did bring up all the interfaces. So we see an Ethernet link. We have a PCI Express I measured pretty good with a switch device, and that's pretty okay. But there are some issues on the card which we are currently struggling with, and Intel helps us out. So yeah, we're not sure what happens there.
I see.
So there is some problems with the JTAG chain, for example.
Well, I guess they're not big enough problems to prevent you from programming the FPGA.
Depends on the board.
Okay.
and the programmer, and we don't know yet.
Man. Okay.
This is the type of issues to get into with.
I see. Well, at least you have a couple of boards to play with and not just one. Don't have one board driven. Why is the JTAG chain on this one not working? You have several that you can check them all and go, okay, it's working on these 2, but not on these 3.
Yeah, so there seems to be some differences depending on various parameters. And we're currently.
I guess the question is it like a manufacturing issue, or is it a a design issue, or maybe you just need to add some buffers, I don't know.
Yeah, we'll see.
Right.
So once we came up with a solution, then I guess we're ready.
Well, I guess if we're talking about boards, Spencer's on here too. We got a board designed for the motor controllers that we need for our project. That's what the carrier board looks like with the Trends electronic SOM. So Spencer's on the call right now, designed the carrier board here, and Spencer's been working on getting the SOM operational, and I think we're starting to get some signs of life out of it, right, Spencer? We got the Linux running on there, and we're getting the gigabit ports operational little by little.
Yeah, pretty much So the Linux is operational, and then I have the Ethernet is I got when I assign static addresses, it works, so it's fine in that respect.
Yeah, so that's a head scratcher. So the interesting thing is with the little switch chip we put down on there, it's showing up with the DSA, the distributed switch architecture. So you've had to figure out how to properly configure that. I guess partially that's done through the device tree, and it seems like partially that needs to be done through the network interfaces configuration file, at least to get it in the proper bridge mode. And then, yeah, right now it seems like you can set an IP address and ping, but for some reason DHCP isn't working. So not sure what's going on with that yet, but that's better progress than before. We managed to get there was, I think there was, Spencer, there was some like change in the device tree options or
Yeah.
something in terms of getting the PHY configured properly.
Yeah.
Pointing so that this is the switch chip PHY pointing back at the SOM. Had to change one of the delay settings, and that wasn't getting set right. But turns out we were using the wrong parameter. I think they changed that. Yeah. So anyway, making some progress, and we are using MLE's make files for that, right? For the Pdp side. Yeah.
Mhm.
So yeah.
Yeah.
Those
Actually,
those have been helpful.
so a question I had for MLE is like, so I know for Yocto, you could like bit bake like tiny components, but is there an option to do that with your make file? So like if I need to rebuild like the device tree or something, could I just make that component instead of rebuilding the whole image?
Yeah, that's definitely possible. But yeah, in the end, it doesn't have to do anything with the make file. The point here is we decided to keep the make file rather simple or minimal, and kind of not add a whole lot of targets, which then just trigger certain commands to, for example, build the device tree or clean a certain application, rebuild a certain application. For us, the make files are a means for rebuilding a design, or in this case images, from scratch in a defined way.
So it's more for like production kind of stuff where, you know, you just want to build the latest version from scratch.
Yeah.
If you're doing development stuff, maybe you want to interact a little bit more with Yocto directly.
Or in this case with the Peta Linux tools themselves. I mean, again, they are a kind of wrapper around Yocto. And in particular, or for that example of rebuilding the device tree, you would do the Peta Linux build command and give it the recipe name and the action you want to do. In this case, force or recompile. That's at least a theory, works with most recipes from Yocto terms, but actually for the device tree, I guess it works, but the device tree is kind of a very special thing, since it also involves calling parts of the Xilinx tool chain of what was earlier called the XSDK for actually generating a device tree. So I'm not 100% sure about the device tree. It can work,
it's okay.
But not sure. The other point is, you definitely have to extract the result then from the internal build directories, or put in other words, from the deployed directory, I would say, because usually with Peta Linux you get your images from the images/Linux directory. And I think that one is only populated when you do make package boot. and not after just rebuilding the device tree or whatever. So in the end, finding the file in all those directories, yeah, might not be intuitive, but is should be doable, I would say.
To be honest, I don't think the hard part is necessarily rebuilding the whole shebang, right? I mean, running the build process is fine. The issue is having it rebuild a particular piece. So if that means we need to do like some sort of a clean of a particular piece in order to get it to rebuild just that piece, I don't know if there's a way to do that.
Yeah, that's
It seems like
that's
the
the
only thing
issue.
you can really do is clean the whole thing, right? You have, I think, what, the Mr. Proper target or something, which like deletes everything, which is quite
Yeah,
annoying because that gets rid of
definitely, yes.
all of the downloaded files. Which
Yeah,
is,
I mean,
which is a
in
pain.
theory, Peta Linux and Yocto should be able to do incremental builds and detect when something changes. In my experience, the device tree changes do get recognized by this incremental build feature. I didn't have that much problems. If I suspect that every time I suspect that there's a problem with rebuilding, I definitely do this forced clean of a package. As I said, with a peta linux -build command. And there you say -c for component, and then you need the recipe's name, which is device -tree, I guess. And then you have a -x for the action, which then is clean, and you might want to add a -f to force it. And in the end, all that does is call the appropriate Yocto or even bitbake command, of course. And that did help, definitely. And I would say it really cleaned all the intermediate files from building the device tree in this case. Before that point in time, and mostly then issuing or triggering a build of the whole image, rebuilds the device tree in a okay form. And yes, there are cases, of course, where I also just go ahead and clean the whole thing, and I'm even doing more than just Mr. Proper. I do not really trust Peta Linux to really clean something. Usually we have Git, and well, there's Git clean, which really wipes away anything.
Worst comes to worst, you can always just delete it and check out a new branch, right?
Yeah, okay.
Okay.
But
yeah, thank you very much.
To summarize, the incremental build feature, in my experience, works quite good. As soon as there's a slightest doubt, then of course I usually don't check around much or try things. I just clean it and rebuild it.
Okay. Yeah, thank you. Yeah, that makes sense.
Do you know if there's a way of doing like a make Mr. Proper that doesn't delete downloaded files?
Oh, good
or a way to
question.
preserve the downloaded files?
Yeah, I mean, you
because
can
the
move
issue is not so much how long it takes to download the files, it's just sometimes one of them fails to download properly, and then everything gets screwed up until you do another make Mr. Proper and restart again. That's annoying.
Yeah, that interesting problem. I definitely never had that screwing up the download or whatever internet outage causes. Then
But this
for
seems
the
to be like an
build to
internet
be,
outage, just like one particular file just fails to download for some reason. It's just like, I don't know why that one file failed, but
yeah. Okay, then the build
Anyway.
process fails. Okay, but triggering another build should then try to download the file again.
Right, but it's like if I want to do like a make Mr. Proper to, clean all of the build files, but without deleting all the download files. Do you know if there's a way to do that?
No, but that's a good question. All I know is that you can download all the downloads there are, have them locally in one solution. The other solution is to move the download folder out of the project directory and point it there, and then that separate directories should be killed, I guess.
Okay, that's not a bad idea. Yeah, so if it's outside of the tree, then it won't get hit by a make clean. Yeah. I guess actually the issue is not so much the downloads, but it's the cloning that takes place. It clones like several Git repositories, and those take way longer than just downloading files. But yeah. Okay.
I guess it also depends which mirrors are selected. I mean, the Yocto system has this mirror selection going on. Can choose from several sources. Yeah, from my experience, the downloading wasn't that big of a deal.
All right. Well, thanks very much for answering some of the questions we've had on our side.
Yeah,
about,
on that note, you're right. I noticed that with the Pdp package you added in the master branch to the ZCU build, for whatever reason, Yocto wasn't able to download it. It said, well, the server went away, and I thought, well, that's SourceForge. The server didn't went away. Yeah, and just triggering it again, it was fine. It downloaded and built the whole thing. But it's a rare case for me, download issue.
Yeah, I guess it's more of a fail early kind of thing. Like, I think what'll happen, it's like that'll fail to download, but then it's still like downloading some Git repository for like 10 minutes. I got to wait for that to finish and then restart it again. And then it downloads the one file and then continues. So
yeah, well, that's
I don't want to kill it while cloning the Git repository, because then I think it'll get totally screwed up. But anyway.
Yeah, by the way, the other thing you can move out of the build directory or the project directory is a thing called the state cache. This records also compilation results. Of course, it takes checksums and then knows when it has to rebuild something. So I don't do that regularly, but I did it in the past to move the download directory and the state cache out of the project directory. And I guess both directories can even be shared. So if you have multiple checkouts, multiple things going on, you can point to the same directory, to the same download and the same state cache, because they have locking going on there.
Okay. Yeah, so the only issue that we've run into is that apparently it doesn't like it when you have some of these things on NFS. And in one of our test beds, all of the machines are diskless and boot over NFS. So it becomes a bit of a problem for building stuff.
Okay. Yeah, we gave up on that. We have, every workstation has a local SSD. We don't even build on machines with HDDs for better Linux.
Yeah,
just slow.
Yeah, we'll probably have to come up with a different setup here. But yeah, for that particular test bed, we're more interested in the FPGAs and the machines and keeping everything identical. So if we boot it over NFS, that's great, because we can just reboot everything and they're all running the exact same image.
Yeah, so, definitely. Yeah.
Install a package, it's there for everything. Yeah. but that is kind of a an oddball setup. It also saves cost, right? We have like 9 or 10 servers in that rack. And now you don't have to put 9 hard drives and everything. You just put all nice SSDs in one of them, and then they all boot off the first one, and you're good to go. Anyway, all right. So let's see. Is there anything else that anybody wants to discuss? Been talking about Pdp and system on modules. A little bit different than Corundum usually. All right. Ulrich, did you want to say something, or says you're not muted?
No, I don't think so.
No. All right. Sounds good. Well, if we have nothing else to discuss, then I guess we can call this a successful meeting for this week, and see all of you in 2 weeks, I guess. Thanks to everybody for tuning in.
Thanks, everybody.
See
Have a
you.
good week.
See you in 2 weeks.
And thanks again to Bob for the cards.
Thanks, Bob. Yes,
You
I
bet.
think this card also looks good. And thanks.
Yeah, you bet. Let us know how it goes, and yeah, I'll plan to probably move some of that into our lab too as well. Once you get it submitted up, we'll test it here as well.
All right. Yeah. Yeah, I'm hoping to get that squared away just in the next couple of days. So yeah, I'll certainly let you know on Slack.
Okay,
All
sounds
right.
good.
Great.
Thanks.
All right. Well, see y'all in 2 weeks.
See
Back
you.
to
Thank you. Thank you.
See you.
See you.
Bye.
Yeah, bye.
Bye.